Now, the next part of equilibrium, the second part of equilibrium, is the equilibrium law. This is the calculation part of the topic. Now, a useful quantity in any equilibrium system is known as the reaction quotient, or concentration fraction is an alternative term for it. Now, I've given you the reaction quotient here for the Haber reaction, and it is based on this equation. And you can see pretty clearly what the link is between this equation and this expression. On the right-hand side, on the top of the expression, on the numerator, we have got ammonia squared. And that's because ammonia is the product and there are 2 moles of it. So the moles give us the power and the products go on top. So on the left-hand side, we get the reactants, they go on the denominator, and we see we've got nitrogen, 1 mole of nitrogen, 3 moles of hydrogen. What do we see? Nitrogen to the power of 1, hydrogen to the power of 3. This is how reaction quotients are done. It's the products over reactants to the power of the number of moles. Now, if the system is at equilibrium, the value of this reaction quotient equals the equilibrium constant, a constant for that reaction at a particular temperature. And we're going to be, 99% of the time, we're going to be looking at these systems, calculating these values for a system at equilibrium. So I'll be calling these the equilibrium constant expressions as much more often than I'll be calling them the reaction quotients. So, in general terms, the reaction quotient, the equilibrium constant, is products to the power of the number of moles over reactants to the power of the number of moles. And as I say, that's a constant for a particular reaction at a particular temperature. Note that equilibrium constants change with temperature. Now, we're only really worried about equilibria where we've got reactants and products in the same phase. So for gas phase reactions, we're just looking at the things that are gases. So we ignore solids because the concentration of them doesn't actually mean much. And for aqueous reactions, we include anything that's aqueous, but again we ignore solids because they don't have a concentration, and we ignore water too for an aqueous reaction because water is a solvent. The concentration of water in a solution doesn't change. You've always got whatever the density of water is, something like 58 moles per litre. That never changes, so water is never part of an equilibrium constant expression for an aqueous reaction. It quite often is in gas phase reactions though, but never aqueous reactions. So, let's do a simple example. (2SO2 plus O2 goes to 2SO3) is allowed to reach equilibrium, and we're given the concentrations of everything at equilibrium. That's nice and easy. So first of all, we write the equilibrium constant expression. Products over reactants to the power of the number of moles. Once we've got that, all we do is sub in our concentrations. We've got, they're all concentrations. Nice and easy. Sub them in and solve. Practice doing some of these on your calculator. You've got, lots of terms on denominators and numerators, and you've got powers and stuff like that. So lots of scope for you to make button pushing errors. So practice these. Practice on your scientific calculator, of course, because you won't have your CAS calculator in your exam. Now what do we see? Units are m to the power of -1. Where on earth do we get that from? Well, they're actually derived from the powers in the expression. we've got molar squared over molar squared times molar. So a little indices thing there. So top line, we've got molar squared over molar squared times molar, which you'll remember your index laws. Molar squared on molar cubed. Divide the base, subtract the powers, that's going to give us molar to the -1. So that's how you do the units for an equilibrium constant expression. They change depending on the powers in that expression. Which is probably what's going to appear here, it does indeed. Now, how is that going to change, excuse me, when we change the number of moles in the equation? Here we've halved the coefficients. So when we write the equilibrium constant expression, we're going to halve the powers. And what does it mean to halve the powers? Of course, that means taking the square root. So instead of SO3 squared, it's going to be SO3. Instead of SO2 squared, it's going to be SO2. Instead of oxygen, it's going to be oxygen to the power of a half, which is, of course, root oxygen. When we work it out, that's what we'll get. And note that that is the numerical square root of the original value of K for the original version of the equation. So you halve the coefficients, you take the square root of the equilibrium constant. Don't actually have to work it out again, you just need to do that fairly simple process. And powers work out exactly the same way. You do your little indices calculation and you'll get that. For this one, what have we done here? Well, we've reversed the reaction. That, of course, means flipping the expression upside down. So numerator and denominator swap. That means we're going to swap the value we get. In fact, we'll find the reciprocal of the original value of the equilibrium constant. So it's going to be 1 over the original value. Again, you don't have to calculate again, just find the reciprocal. And that just highlights how important it is to write the equilibrium constant, write the equation with any equilibrium constant expression, because the actual value you get is going to depend on the coefficients you put in the equation, which way you write that equation. Okay, so we've got our system at equilibrium and more gas is added. When the system reaches equilibrium again, we get concentration of sulfur dioxide, concentration of oxygen. What is the concentration of sulfur trioxide? Well, we already know the equilibrium constant, so we can substitute that and the two concentrations we know into the expression. That leaves us with one unknown, which we can solve for fairly simply. So put in all the values we know, leaves us with SO3, well it's SO3 squared, so that calculation will give us SO3 squared, then we take the square root of it and we get that answer. Okay, on to the question. And let's look at a more complex example with a few more of the tricks they put into these questions. So, how is this different? 4 moles of NO2 reacts with 1 mole of O2 and 1 mole of N2O5 in a 2 litre vessel the system is allowed to reach equilibrium. When that happens, the amount of N2O5 is 1.8 moles. Calculate the equilibrium constant. Well, first thing, we're given moles, not concentrations. So at some point, before we calculate our equilibrium constant, we're going to have to calculate concentrations. Divide by the volume, calculate concentrations. So that's a trick you just got to be aware of. But the more serious issue is the fact that all this lovely numerical information we're given is not what's present at equilibrium. It's what happens at the start. It's what's added at the start. It's the initial conditions. What do we know about the system at equilibrium? All we know is N2O5 is 1.8 moles. We don't know how much NO2 or how much O2 is present. But we do know that we started off with 1 mole of N2O5, we ended up with 1.8 moles of N2O5. So we can see that 0.8 of a mole of N2O5 was produced. So by applying mole ratios, we can work out if 0.8 of a mole of N2O5 was produced, we can work out how much NO2 and O2 were consumed. So do a little bit of stoichiometry. It's not difficult stoichiometry, but it is quite difficult to, it is easy to get confused. So we draw up something known as an ice table. So, let's write our equilibrium constant expression. Products to the power of the number of moles over reactants to the power of number of moles, and then we do our ice table. What does ice stand for? Initial, change, equilibrium. There are, of course, multitude of ways you can set out this table. This is a common way, and it's a good way. It's one that works. So, what are we told in our given information about the amount of stuff present initially? Well, what was it? 4 moles of NO2 is reacted with 1 mole of O2 and 1 mole of N2O5. What else does it tell us in the question? How much N2O5 was present at equilibrium? Now we can see from that exactly how much N2O5 was produced. So if 0.8 of a mole of N2O5 was produced, then we can work out the O2 and the NO2. So we can write that in terms of x's. If, looking at the coefficients, if 2 moles of N2O5 are produced for every 1 mole of that and 4 moles of that, then N2O5 is going to increase by 2x. If O2 decreases, because it's a reactant, it's going to go down by x, and NO2 is going to decrease by negative 4x. So we know that 2x equals 1.8. So that means x equals 0.4. So if x equals 0.4, then O2 is going to go down by 0.4. NO2 is going to go down by 4 times 0.4. You can use x's in that row, or you can just do the numbers if you prefer. X's is good because it just is that little bit more systematic, a little bit more logical. Now, once you've got your moles, you've got to remember that's not the final step. You've got to convert them to concentrations. It's easy just to plug those moles into the equilibrium constant expression and you will get the wrong answer. So plug in the concentrations, determine the concentrations, plug them into the equilibrium constant expression, and you will get your answer. So then we've got a question. Which I'll get you people to do. I'll continue these slides just to the end of this section. So do those questions and then come back to this. What does the equilibrium constant tell us? Well, the reaction nitrogen plus hydrogen gives ammonia again. We've got our equilibrium constant expression. If that's a very large number, what does that tell us? If it's greater than, say, rule of thumb, 10,000, 10 to the power of 4, if that's a very big number, that means the numerator is very high. If you've got a very high value on top, you've got very slow values on the bottom. That means you've got virtually all products, virtually no reactants. That means the reaction has essentially gone to completion. On the other hand, if it's less than 1 in 10,000, 10 to the minus 4, that means you've got pretty much only terms on the denominator. Numerator is very low, denominator is very high. That means you've got pretty much all reactants present. That means the reaction hasn't gone at all. You've mixed together reactants and nothing's happened. So anything between roughly 10 to the power of 4 and 10 to the power of minus 4, we consider to be an equilibrium system. So that's where significant amounts of both reactants and products will be present at equilibrium. So if we calculate what we think is the equilibrium constant and the value that we get is not equal to what the equilibrium constant should be, we can tell that the system's not at equilibrium. So we calculate the reaction quotient and a test to see whether the system is at equilibrium is it equal to the equilibrium constant. If it is greater than the equilibrium constant, you've got too much on the top line, you've got too much products, that means the reaction is going to have to go backwards to reach equilibrium. If it's less than the equilibrium constant, you don't have enough products, you've got too much reactant on the bottom, not enough product on the top, so the reaction is going to have to go forward, move to the right to reach equilibrium. So the reaction we're given the equilibrium constant and we get some random mixture of the gases and we want to know whether the system has reached equilibrium yet. So we just plug our concentrations in the equilibrium constant and see what happens. And oh, what a surprise. The system, we get a different value here than the equilibrium constant. So the system's not at equilibrium. Now we look at this value, is it greater or less than the equilibrium constant? Of course it is greater than the equilibrium constant. That means we've got too much ammonia. We need to get rid of some of that for it to reach equilibrium. The reaction will go to the left, go backwards. Okay, have a go at that question And like with all the questions, the 3 lots of questions I think in this topic, submit them on Google Classroom, and when you do submit them, I'll send you solution videos. It's really important. This is a really important topic. It's really important that you have a go seriously at these questions. Want to see solutions in your own words. And like I've said, you get these submitted, you get serious answers submitted, then that'll be satisfactory demonstrating the topic.